Hi guys, welcome back to another video. On today's video, we're going to be talking all about ions and ionic bonding. Alright, so that is 2.4 of your syllabus. So first of all, you need to be able to describe positive and negative ions. And before that, we need to know what ions are. I was just recently doing a video just a few seconds ago, but it got stopped, so we're starting again. Alright, so you need to know what ions are. We know ions are charged particles, okay? They're either positive or they're negative. But you need to know why they're charged. Why do they want to be charged? Why not just be particles or atoms? Why do atoms just want to be charged? So to answer that question, the answer is they lose or gain electrons in order to gain and to become stable. And we know a stable atom has a full outer shell. That means either 8 electrons or 2 electrons on its last outer shell. All right, so to become like those noble gases that have everything that they want and they don't want to react anymore. All right, so now let's talk about the two types of ions, right? So we have ions that are divided into two. We have the anions and the cations. Okay, so anions are positively charged ions. Okay, positive. So an example of this, we could give magnesium with 2 plus, sodium with 1 plus, aluminium with 3 plus, and it goes on. There's so many cations in our periodic table in chemistry in general. Anions are the opposite. They are negatively charged ions. Okay, negative. Example of this, we have chlorine minus, we have O2 minus. What else do we have? We have I think that's all I can remember from the top of my head. So these are a couple of examples that we have here that we can use. All right, so now that is the first point done. You need to know formation of these ions. Okay, so how do they form? All right, we're going to look at that in just a bit. And now you need to know how ionic bond is formed, okay, between oppositely charged ions. And we're going to take the very basic, the very commonly used example, which is ionic bonding in sodium chloride. Okay, we'll get into the dot and cross part in just a bit, but we need to understand where this comes from. All right, so sodium has, we know, 11 protons, hence 11 electrons, right? It's not charged. This is an atom, has equal numbers of protons and electrons, okay? And chlorine here has 17 protons, hence 17 electrons, okay? Now, what are we getting at? Let's go and look into a little dot and cross diagram just here. All right. So in order to, we've seen in a previous video, I'll link it up, which is about electronic configuration. And when you configure your 11 electrons for sodium, that's going to be 11 electrons, which is 2, 8, and 1. All right, so let's put these electrons in. So we're going to use a circle for sodium. So there's 2 in there. In the second shell, you have 8. Pair them up like that. That is 4. That is 6, and that makes it 8. And it just has 1 electron on this outer shell, so 1 valence electron. Now, chlorine here has, we're going to use X, and it has 7 electrons, which will be configured as 2, 8, and a 7. All right, so that's going to start, okay, oh, sorry, apologies. Let's fill that out. That's going to be X for chlorine, okay? Then you need its dot and cross. Okay, so that's how you represent different types of the different electrons of the 2 or 3 different types of atoms. Okay, so your chlorine has, there we go. So you always pair up your electrons, which is, you know, a cool way of doing it. and then it has 7 here. So it just has 6 here and just 1. So what do we notice here? We notice that sodium here has this one little electron in its valence shell. And chlorine has just this one spot missing. It's saying one spot missing. What do we see in common here? We know both elements of sodium, both atoms of sodium and chlorine. Okay, sorry. Both atoms do want a fuller outer shell electron. Now, what could happen? Okay, how do you lose or gain electrons? Sodium could say, I could give my electron right here to chlorine. It can lose its electron and give it to chlorine right here. What does this mean? It means if it gives chlorine here, then we have an ion formed. Sodium here is losing an electron, and chlorine here will be gaining an electron. So chlorine will have a fuller outer shell electrons, 7 of its electrons on an outer shell, and it's 1 electron that it's gained from sodium. And sodium will lose this electron, and because there's only 1 electron on this shell, the whole there's no other electron in this outer shell and the third shell, so it's going to lose the third shell, and it's just going to have 2 electronic shells. Okay, I know that's a lot to take in, so let's kind of like break it down. In your exams in chemistry, you're not expected to draw, when you ask for dot and cross diagrams, you're not expected to draw this whole, like all the electronic shells. All you need to draw is the outer shell electrons. So let's take this revised, this electron to a revised smaller version. So we know sodium has an outer / valence shell of 1. Oh, sorry. Yeah, technically. So we want to draw the inner one. Do we want to draw the inner one? No, that's okay. Okay, we want to draw the inner one because it just has 1 electron on its outer shell. So we're gonna draw the 1 to the 8 electrons, and then the 1 here. All right. Chlorine, we can just draw that outer shell electron, which is 7 valence electron. Just this one. This last shell you're going to be drawing because only your last shell is involved in ionic bonding or any type of bonding or reaction because it contains the valence electrons which are involved in reactions. All right. So chlorine, we're going to put our X here. There's only 7 electrons here. Okay. So now this is how you easily draw it, and usually when they ask you to draw it, this is the one that they want because it's easier for you and it's easier for the examiners as well. So now this, when it's bonded with the way you want to draw it, you need to be careful, okay? We know sodium has all its 8 electrons after losing, this is its second shell, mind you, because it's lost its 1 electron that it had on its third shell. So now it only has two electronic shells with all of them filled up, so it's stable now, okay? And here you want to put in the charge. Okay, what is the charge of sodium? Now this is, be careful. Now a lot of people would think a positive charge is going to be when you want electrons, but no, a positive charge means you've lost electrons because electrons are negatively charged. By losing electrons, an atom can become positively charged, or else known as a cation. Okay, and again, a negative charge will be an atom that has gained an electron. Now, I would like you to pause this video and try to think, which one do you think is going to be the positive one, and which one do you think is going to be the negative charged electrons? Okay, now I'm going to answer it quick here. The positive charge is sodium. This is your positive charge because it has lost an electron. And how many electrons did sodium lose? There we go. That's your 1 electron right there. So it's going to be a +1. And in chemistry, and just mathematics, if you just have 1, you don't have to write it because it's just like a known fact kind of thing. So you just can write it as a plus, okay? Just plus, and that means just a +1. And chlorine here also has gained just 1 electron, which is here from sodium. and it's going to be written as, so we already have our 7 electrons of chlorine, and it's gained 1 from sodium, and it's going to be negatively charged. To remind you, these brackets are needed in ionic bonding. So this is how you can do dot and cross diagrams. So if I go back to my syllabus, I think we covered quite a lot of these. So ionic bonding, okay, let me use a different color. At your level, you need to know that they occur between oppositely charged, I was going to say particles, but oppositely charged atoms / ions. They become ions, sorry. Oppositely charged atoms. So you have positive in sodium, chlorine is negative. So positive and negative is what you have your ionic bonding. And this results in a strong electrostatic attraction. Okay, but due to this type of bonding. Now your keyword here is electrostatic and you're strong. Whenever you want to describe ionic bonding, you need to talk about these 2 points. Your bonding and attraction occurring between oppositely, okay, charged atoms. And what does it result in? Strong electrostatic attraction. There we go. So if we go back to our syllabus, we have ionic bonding is a strong electrostatic attraction between oppositely charged ions. This always comes in a definition question, which is about 2 or 3 marks. Now you need to talk about ionic bonds formed between group 1 and group 7, which is the sodium and chlorine one. And now let's talk about the different properties that these ions exhibit because they have this strong electrostatic attraction, okay? Let me use a different, okay, we're going for blue. Properties of ionically bonded particle. Oh my god, do I just forget spelling? Why is this? Bonded particles. Now, because these ions an ionic bonding oh my god, what is going on today? Ionic bonding results in strong, there's a little bit of glitch, strong electrostatic attraction. Oh my god, sorry, attraction between oppositely charged ions or charged atoms. You're gonna have, I don't know, let's use that little cute green right there. Is it green? I'm guessing like a minty green. So because you have a strong electrostatic attraction between oppositely charged atoms, you have they have very high melting point and boiling point. Now, in a question, when you are asked to mention properties, you need to talk about the high melting point and boiling point. And how do you describe this property? You refer back to the type of bonding and the properties and the characteristics of this type, the ionic bonding. Okay. Now, the second point you want to talk about is it can only conduct electricity when liquid, you can also call it molten, or in aqueous solutions, dissolved in aqueous solutions. And when you're asked why do we really care about this? Like, am I supposed to be worried? Is this my problem? Kind of. Okay. So the reason of this is because in solid um what sorry ionic compounds, let's zoom in a little bit, do not have electrons floating around to carry charge. And we know in order to conduct electricity from one block to another, you need some things, little things to carry charge, okay? And there's no electrons free, so you don't have any way of conducting, okay, and carrying charge. So that is a little bit about the properties of ionic bonded particles. Slash. Let me use that one. That's such a pretty color. Or ionic compounds, right? Also known as ionic compounds. I'm gonna go through this so quickly. All right. So, we have discussed these two properties: high melting points and good electrical conductivity when aqueous or molten, and they are not good when they are solid. All right. We talked about explaining the structure and bonding in ionic compounds and how you can explain why these properties of ionic compounds. Okay, we've done that. And have we done giant ionic lattice structure of ionic compounds and how they are arranged? Yep, we have done that. And we have described the formation of ionic bonds between metallic and non-metallic elements? Okay, we can just revise this. So usually our cations tend to be our metals, right? So magnesium we know is a metal, sodium is a metal, aluminum is a metal. They are all very commonly metals. And our anions are usually tend to be non-metallic. Okay, so an ionic bond essentially happens between a non-metallic and a metallic. Let's call it metallic elements. All right. Now, do we want to talk a little bit about the giant ionic structure? Yes. So let's take sodium and chlorine, the same example. So I'm going to draw the all. Okay, excuse my circles. I'm a good artist or any artist of any sorts. Okay. Oopsie. Okay, if we want to draw a little and show a little bonding between these sodium and chlorine, we have Na plus and the Cl minus is on these little ones. Our electron, oh, I was going to say electrons, sorry. That is non-metallic bonding. Apologies. There we go. So this is like your giant ionic lattice. Lattice just means regular arrangement, okay? It's regular, it's the same. Nothing very like extraordinary, you know? So yeah, that's pretty much it. What am I missing here? I think that's all. That's pretty much it. So thank you guys for coming. I don't know if that was quick or not, but if you have any questions at all, you can refer and you can ask in the comments below. Thank you guys for watching, and I will be posting the notes on the description below. And yeah,